workbench power supply, a handy tool for your projects. Today, I want to show you how useful a bench power supply can be, some tricks and tips, and how I use one of my own electronic projects to test, validate, or troubleshoot some ideas. I am going to use a Multicomp Pro power supply, more exactly the MP710081. This power supply was supplied by Element 14 as part of the road test program. But before we start, let's answer a couple of questions as a short introduction. So, do I need a power supply in my workbench, and what can I do with it? A power supply provides an easy way to troubleshoot or validate your electronic projects on your workbench. Some electronic projects could run from a direct power source connected to your wall, outlet, or batteries, among other myriad of possibilities. And a final product certainly will have a nice power source. Maybe always connected with or without a backup battery, or running from a battery and maybe some solar power to recharge it. But at the end, all of them need a source of power. Regardless of your final goal at the beginning, you will probably start with a breadboard, maybe a development kit, and maybe some kind of sensors or actuators. Sometimes the power supply that comes with your development kit will suffice most of your needs. However, as things become more complex or your ideas go crazier, you will end require something else to test them, like a high voltage for a proximity sensor that works on the range of 6 volt DC all the way up to 36 volts or more, or high current and lower voltage for a high power laser diode. Or maybe you just want to control some DC motors. It is common that a project will require different voltage for different elements. You can have an Arduino daughter board that requires 5 volt DC connect to a Raspberry Pi that only works at 3.3 volts. Or you want to test a sensor first before connecting it. And maybe that sensor requires different voltage for proper operation, like this Panasonic particulate sensor that requires 5 volt DC and 3.3 volt DC. Or you just want to test or characterize a DC motor or some actuators. And maybe all of this just belong to your new project. And one thing about all this is that they have different power needs, different voltage and different current. A variable power switch come handy in these cases. You can generate different voltage or have more than one different voltage output. With a nice workbench power supply, it is also possible to limit the current to avoid damaging the circuits. Do your test before connecting everything and avoiding costly mistakes. But there are several supplies out there, when the question will be, which one do I need? What to look in a power supply for my workbench? Go and write down your requirements. What kind of sensors are you going to use? Are you planning to have DC motors or other power-hungry devices? DC motors can have different requirements, from hundreds of milliamperes and low voltage all the way up to 48 volts DC with 3 to 8 amperes in some cases. And although they are usually controlled with PWMs, to characterize them or test them, a variable power supply is really handy. And what about your system board? Don't underestimate your system current needs. Remember that power equals voltage times current, so 30 watts at 30 volt DC is 1 ampere, but at 3 volt DC it is 10 amperes. Take note that some embedded system boards could easily require more than 10 watts of power, and they usually work with lower voltage like 3.3 volt DC. Of course, you will probably need multiple outputs like fixed 3.3 volt DC, 5 or 12, which are common, and variable outputs. Other specifications you can look at are noise, but usually your embedded board already has a regulator, and for the sensors you should provide the required components layout, accuracy and fine-tuning, and voltage current regulation variation with load, among some other parameters. The MP710081 Multicomp Pro power supply is a small 100 watts switching power supply with current limiting control. It can output at the same time 3 different voltage, 1 variable and 2 fixed. As mentioned earlier, this power supply was provided by Element 14 as part of the road test program. There are 3 different variations of this model, and they differ on the variable output power specification. The 79 has a max voltage of 20 volt DC with 5 amperes, the 80 36 volt DC 3 amperes, and the one using in this video, the 81, has a 60 volt DC and up to 1.6 amperes. So, okay, let's take a look at our power supply. So as mentioned on the specs, we can change the voltage from 60 all the way down to 1 volt on our variable output, and we can have a range of 250 milliamperes all the way to 1.6, 1.8 amperes in this case. We also have a fixed 12 volt 0.8 amperes DC voltage output and a selectable between 3.3 or 5 volt DC 1.8 amperes, and we can select that on a small switch that is on the back of the power supply. One important characteristic about this power supply is that the three outputs are isolated. What that means is that we can use different several configurations to get like minus 12 voltage or increase above the current range the voltage as required. That means that we can connect the positive of the aux to the ground of the 3.3, which will make this a minus 12 3.3 configuration, and any other combinations that we can do. Okay, now some time for tips and tricks. But first, some recommendations. Always unplug the bananas before turning on the power supply. Set the voltage and current limit if required before enable the output. This I have here a small button that you can enable, disable the output. Work on a cool area, which basically means work between the specs of the power supply. In this case, you can work between 31 Celsius, 80% relative humidity, and up to 40 Celsius, 50% humidity. One final recommendation or piece of advice: if you really need a precise measurement on the voltage or the current, use a scope or a multimeter, which will give you more precision on that kind of stuff. Okay, so time for some experiments. Here we have a 10 watts, 10 ohms resistor, and we are going to set our power supply, let's say, to 10 volts and the max current. So let's plug in the cables. Okay, so and after everything is connected, we double check that everything is okay, and then we can just switch on the power supply here. Okay, so we can see that it's more or less around the 1 ampere. Of course, the resistance has some tolerance. It's not 10 ohms exactly. And then we can increase the voltage as we please here. Right? 12 volts. And then start that. So now, this resistor is rated 10 watts, which means if I'm going to output 10 volts or more, then I'm going to drag 1 ampere, which is the 10 watts. So I should not work past that. So what I can do is now going down, I set the maximum output to 1 ampere, 10 volts, which give me 10 watts. And let's see what happens. Okay. So now everything is set properly. And we are beginning to increase the voltage. As we can see, let's go back a little. Okay, so here you're going to see CV, which stands for constant voltage. So what is going to happen is, after I begin to increase the voltage here, the current consumption is going to increase too, and all the way up to the 1 ampere I have limit here. As soon as I reach the 1 ampere, what is going to happen is that the power supply is going to switch to constant current here. So now, if I try to increase the voltage, say 11 volts, nope, the power supply is going to tell me no, you can't, and I'm going to limit your voltage on that. I can go all the way up, and still it will limit the voltage because now it's a constant current power supply, which is good. I protect my circuit here, which is be really hot right now, but within range, and we are happy. Now we put everything off. This is going to be kind of hot right now. Let's try to check that. So we have this here too. Okay, DC motors, one of my favorite topics. So DC motors are usually controlled using PWMs and a microcontroller. But most of the time it's better to test them first to verify their specification. One critical one is the minimum voltage it requires to start to rotate. And this is when a power supply, variable power supply, comes really handy. So let's do this. This one I recycled from some printer, I don't remember. And let's do something to so we can notice more easily that is actually starting to rotate, right? Let's mark it here, the X. Okay, so let's set our variable output to 1 volt DC, and the current we just set to the maximum. We don't care about the current at the moment. And then what I'm going to do is start the current. You see, the motor didn't start. We are going to increase the voltage. You see, it began to rotate a little, but it was not enough. So at some point, it's going to start to rotate. And that was like 3 volts. And you can see that now I'm lowering the voltage and it's still rotating. And I'm pretty sure I can begin to go down, and the motor will still rotate without any issues. There you go. Slow, but still rotating. 1.5. Even all the way down. There you go. Stop now. And now you can see that if I try to increment the current, it will not start. So what I'm trying to find is the minimum voltage that the motor requires to start to rotate. And that is important because when I'm going to use the PWM, is going to give me the minimum duty cycle I can do for this motor. So, okay, let's turn this off. And let's say I think it was 3 volts, so we can try 2 volts here, and then we start, and it start rotating. Good. Turn it off. So that was too high. Let's go to 1.5 and see that I'm turning on and off the power supply for this. I turn on 1.5, but didn't rotate. Now I can increase 1 by 1, 1.6. You see now I'm getting some current consumption, but still no rotation. 1.7, 1.8, 1.9. There you go. It begins to move a little. So I'm going to do is stop there, turn it off, and then turn it on again. And no, it didn't start. So let's try 1.2. Turn it off, turn it on, and then it's, yep. So it's 2 volt DC, and it's consuming around 60 milliamperes. Can turn it off, and turn it again. There you go. One interesting thing you can notice here, let's go back to 1.6. You see, every time I turn it on or off, it tries to start, but it can't. And if I do this, there you go, start rotating. If I stop it, then stop. It doesn't have too much torque, but there you go. So, just to be sure, one last time, 2 volts. And there you go, find it. Okay, now let's try to go probably to 6 volts. I think 6 volts should be okay as a max. And there we go. Nice. Okay, now let's try a gear DC motor. Let's start with 1 volt and let them limit the voltage. We hit start. I'm pretty sure probably it's not going to start, but wait, let's check it. There you go. You see, it's going all the way to almost 2 amperes. Turn it off. Split 2. There you go. And 2 is working. What happens if I just lower down this? 1.9, 9.8. 5, 3, 2. There you go. So by the way, this is a year motor, and you can see that it's consuming 600 milliamperes, and it's because the year here is really, if I try to stop this guy here, I will not be able to stop it easily like the other one, and that's what a year motor means. Let's try with 1.8 to see if it starts. There you go, started. What happened with 1.5? Okay, 1.5 worked too. 1 volt. No, 1 volt definitely doesn't work. 1.3. Okay, good. But 1.3 more or less. The reason I'm showing this one is for the following. Let's start with 3. It's working fine, no issues, and you see here is around 700 milliamperes. And what I'm going to do is to limit with this to 1 ampere. And let's see what happens. Okay, the motor was not able to start and it's stalled right now. So what is happening is that the motor to start rotating need a peak current, and the peak current probably is, let's try 1.5. No, 0.6. Yep, 0.6, around 0.6 amperes, right? So what I just find here is that when I'm going to put this in a, I don't know, using batteries or another kind of power supply, whatever I want to do with this motor, my power supply have to be able to provide a peak of 1.6 amperes for this motor to start. If the power supply cannot provide that, then I'm going to be in trouble and the motor is never going to start. Regardless, even if I put a lot of voltage here, that guy is not going to go anywhere if I am only able to provide 1 ampere, right? Let's see if I try 6 volts. Nope, no luck. Why? Because I need to provide 1.6, maybe more for the voltage. I think I'm not going to be able to with this one. Oh, there you go, 1.8. So again, I need a peak current, 1.8. If I put 1.6, start okay. There you go. If I go this 1.5, wait a little, no luck. And even if I increase this to, I don't know, 10, this motor can work up to 12. So no, no luck here. 1.6. Yep, 1.6 works perfectly, like a charm. No big deal. Voila. So, in summary, in this case for variable power supply, I really like them because they allow me to find some parameters that I require for my DC motors. Minimum peak current to start a year motor, minimum start voltage for some other motors, and that's pretty nice. Well, sky is the limit and time is short. I hope you enjoyed this uh, short demo tips tutorial about power supplies. Again, thank you to Element 14 for providing this nice power supply and for the opportunity to do this video. I hope you enjoy it. Would you need a power supply? If you do projects with electronics, yeah, probably you will need one. And I just wish you the best of the luck. Again, comments are welcome, and hopefully in the future I will be able to have more time to do more tips and tricks. I also did a video about the USB port in the power supply. The video is 10 minutes long, so I didn't want it to edit it or put it in this. So it's in the link down there in the description. If you are up to, just watch it. I hope you enjoy it. Thanks.